Welcome back to the deep dive. This is where we take the sources you send us, unpack them, and really try to get to the core knowledge together.
Yep, making complex stuff accessible.
Exactly. So today we're jumping into, well, ancient Indian mathematics. We're looking at Aryabhata's Aryabhatiya, specifically chapter 4, the Gaṇitapāda.
And the star of the show today is his Kuṭṭākāra algorithm. It's quite something.
Now, some of you might remember we talked about Aryabhata before, I think it was, episode 43, from the pasted text info you sent.
That's the one. We covered his ideas on the Earth spinning, epicycles for planets, calculating eclipses, his value for pi even.
Oh yeah, and trigonometry too, right? From the Gola section.
Right, Gola 10 and 12. But today, the Kuṭṭākāra, it's this really elegant piece of algebra.
And it's not just, a historical curiosity. The sources really emphasize this as a major contribution to algebra globally. Really shows the sophistication back then.
Absolutely. It's a landmark. So for this deep dive, we've got, I think, 3 main questions we want to tackle based on the materials.
Okay, what are they?
First, what kind of math problem does this Kuṭṭākāra thing actually solve? Like, what's it for?
Right.
Second, why was this so important for Aryabhata? He was an astronomer, so why did he need this algorithm? What's the connection?
The practical application. Makes sense.
And third, why should we care today? Does the logic, the thinking behind it, still show up anywhere? Does it still matter?
Great questions. Okay, let's start with the first one then. Segment 1, what's the problem? Linear indeterminate equations. That phrase sounds a bit intimidating.
It does, doesn't it?
Oh,
but
yeah.
we can break it down. Let's think about a simple equation first, maybe from school algebra, like 2x plus 3y equals 7.
Okay, I remember things like that.
So that's linear because the x and the y are variables. They aren't squared or cubed or anything tricky. Just x and y, power of 1.
Simple enough. Unlike, say, x squared plus y equals 5, that wouldn't be linear.
Exactly. Now, the indeterminate part, that basically means we've got more unknowns, x and y, 2 of them, than we have equations linking them. We only have the one equation, 2x plus 3y equals 7.
And if x and y could be anything, like fractions or decimals.
Then, yeah, there'd be endless possibilities, an infinite number of pairs for x and y that make the equation true. Drawn on a graph, it's just a straight line, right? Infinite points.
Right. But that's not what the Kuṭṭākāra is about, is it? The source material highlights something specific.
Precisely. The absolute key constraint here, the real challenge Aryabhata was tackling, was finding integer solutions.
Integers. So whole numbers. Positive, negative, or 0, but no fractions, no decimals.
Exactly. Whole numbers only. So back to our example, 2x plus 3y equals 7. Can we find whole numbers for x and y that work?
Let's see. If x was maybe 2, then 2 times 2 is 4. We need 3 more to get 7. So 3y should be 3, which means y would be 1.
Perfect. So x2, y1. Both integers. That's one solution that Kuṭṭākāra could find. 2, 1 works.
Okay, that makes sense. But are there always integer solutions?
Good question. And the answer is no. The source gives a really good counterexample. 2x plus 4y equals 7.
2x plus 4y equals 7.
Let's think. 2x is always going to be an even number if x is an integer, right? Right. 2 times anything whole is even.
And 4y, well, 4 times any whole number is also going to be even.
Tricky, yeah.
So the left side, 2x plus 4y, is the sum of 2 even numbers. And adding 2 evens always gives you another even number.
Always.
But the right side is 7, which is odd. You can't have an even number equal an odd number.
Exactly. So for 2x plus 4y equals 7, there are absolutely no integer solutions possible. It just doesn't work with whole numbers.
So the Kuṭṭākāra wouldn't find a solution there because one doesn't exist.
Precisely. It finds them if they exist. So, boiling it down, the Kuṭṭākāra is a systematic procedure, an algorithm for finding integer solutions, x and y, to equations of the general form x plus by equals c, where a, b, and c are known integers.
X plus by c. Okay, that's the core problem type.
Yep. And it's more powerful than it looks because, as the source mentions, this structure, this type of problem, pops up in other places too.
Like the Chinese remainder theorem connection you mentioned earlier.
Exactly. That's a really key insight from the source material. It shows the algorithm's flexibility.
Can you expand on that a little? How does finding integer solutions for x plus by equals c help with, like, finding a number with specific remainders?
Sure. So the classic remainder problem is like, find a number that leaves, say, a remainder of 2 when you divide by 3, and a remainder of 3 when you divide by 5.
Okay.
You can actually translate those conditions into mathematical statements called linear congruences. It looks a bit like equations, but involves remainders. So n is congruent to 2 mod 3, and n is congruent to 3 mod 5.
Right, modular arithmetic, working with remainders.
Exactly. And solving a system of these congruences, finding the number n that satisfies both, often involves steps that are mathematically equivalent to solving a linear indeterminate equation of the form x plus by equals c. The underlying principles are deeply connected.
Wow. So the Kuṭṭākāra is kind of a master key for a whole class of number theory problems, not just the obvious algebraic ones.
You could definitely see it that way. It tackled a fundamental structure in number relationships.
Okay, that really clarifies the what. Let's move to the why. Segment 2. Why astronomy? Synchronizing cycles. Why did Aryabhata, the astronomer, need this mathematical tool so badly?
This is where it gets really fascinating, I think. Because, astronomy, especially back then, was fundamentally about cycles. Observing them, understanding them, predicting them.
The sun cycle, the moon cycle, the planets,
Yeah.
they all move at different speeds, right?
Precisely. You have the sun's apparent yearly motion, the moon whipping through its phases roughly every month, and then the planets Mars, Jupiter, Saturn, etc., each with its own distinct orbital period, some much longer than others.
And astronomers needed to know when things would line up.
Exactly. Alignments were critical. The source points out several key examples. Think about conjunctions when the sun and moon appear close together in the sky.
That's crucial for knowing when new moons happen and for predicting solar eclipses, right?
Spot on. And then oppositions when the Earth is between the sun and moon.
Full moons and lunar eclipses.
Correct. And it gets even more complex when you want to predict when multiple planets might align in the sky or return to certain positions relative to each other and the stars. These are much longer-term calculations.
So finding these alignment points involves figuring out when different cycles with the different lengths kind of meet up again.
That's the core of it. You're looking for a point in time, measured in a whole number of days or years or some other unit, where multiple cyclical processes simultaneously reach a certain state or configuration.
And that sounds like, well, it sounds like the kind of problem we were just discussing, finding integer solutions.
It absolutely is. Imagine cycle A takes A days and cycle B takes B days. Finding when they align after some number of cycles, maybe with some offset C, often translates directly into an equation like x plus by c, where x and y represent the number of full cycles completed.
Okay, I see the connection now. It wasn't just eclipses and planets, though, was it? The source mentions calendars, too.
Yes, a huge practical problem. Most ancient cultures, including in India, grappled with reconciling solar and lunar calendars. A year based on the sun doesn't contain a neat whole number of months based on the moon's phases.
Right, the lunar months drift against the solar year and the seasons.
Exactly. So they needed a systematic way to figure out when to insert an extra lunar month, the source calls it adhimāsa, to bring the calendars back into alignment. This wasn't just guesswork, it required calculation.
Finding the right number of years after which adding a whole number of extra months brings things back in sync. Sounds like our equation again.
It really is. Calculating the frequency and timing of these intercalary months relied on solving these kinds of number problems. We apparently touched on this back in episode 5, according to the notes.
And there was another calendar thing, too. The avamarātra.
Right, the omitted or skipped lunar day. That arose from the slight difference in length between a mean solar day and a mean lunar day, a tithi. Over time, these small differences accumulate, and occasionally a lunar day designation is skipped in the calendar count to keep things aligned observationally. Calculating when these skips should occur also involves
Finding integer solutions where different cycles reconcile.
You've got it. All these astronomical and calendrical challenges, alignments, intercalations, day adjustments fundamentally boil down to finding whole number solutions that synchronize different periodic phenomena. The Kuṭṭākāra provided the mathematical engine to do that reliably.
So it wasn't just theoretical math, it was a critical tool for the applied science of astronomy and timekeeping.
Absolutely essential. It gave them predictive power based on calculation, not just observation.
Okay, this makes the algorithm feel much more grounded. Let's get into the algorithm itself then. Segment 3. The algorithm, the principle. The source warns that explaining the exact steps verbally is tough.
Yeah, it's definitely something easier to grasp, visually perhaps, seeing the steps written out. But we can definitely get the core idea across.
The name itself, Kuṭṭākāra, meaning pulverizer or breaker. That gives a clue, doesn't it?
It really does. It suggests a process of breaking something down, pulverizing it into smaller pieces. And that's essentially what the algorithm does to the problem x plus by c.
It takes the coefficients, a and b, and does something with them repeatedly.
Yes, The process is remarkably similar in spirit to something called the Euclidean algorithm. Are you familiar with that?
Vaguely. Isn't that for finding the greatest common divisor, GCD, of two numbers?
Exactly. The Euclidean algorithm finds the GCD by repeatedly dividing the larger number by the smaller number and taking the remainder, then repeating the process with the smaller number and the remainder and so on until the remainder is 0. The last non-zero remainder is the GCD.
Okay, so the Kuṭṭākāra uses a similar repeated division idea.
It does, but it cleverly keeps track of the quotients at each step as well, not just the remainders. Let's use the source's simple example. 7x plus 5y equals 1.
Right. A7 equals 5, C1.
You'd start by dividing the larger coefficient, 7 by the smaller one. 7 divided by 5 is 1 with a remainder of 2.
Okay, quotient 1, remainder 2.
Now you repeat the process with the previous divisor, 5, and the remainder 2. 5 divided by 2 is 2 with a remainder of 1.
Quotient 2, remainder 1.
Now repeat with the previous divisor 2 and the remainder 1. 2 divided by 1 is 2 with a remainder of 0.
Quotient 2, remainder 0. We stop.
We stop the division part here. The crucial thing is that through this process of reducing the coefficients using division and remainders, you've essentially transformed the original complex problem into a series of linked, simpler problems.
And that last step, where the remainder became 1 just before the 0, is often key.
Yes. Reaching a remainder of 1 is often a target, especially if the original C was 1, because it leads to a very simple equation where you can easily spot an integer solution. If the final non-zero remainder before hitting 0 wasn't the divisor of C, then you'd know there were no integer solutions anyway, connected back to the GCD idea.
Okay, so you pulverize the problem down to something simple, where you can see a solution. But that's a solution for the simplified problem, right? How do you get back to the original x and y for 7x plus 5y equals 1?
That's the second brilliant part.
Yeah.
You work backwards. You use the quotients you recorded during the division process.
The 1, 2, and 2 we got?
Exactly. There's a systematic way, often presented in a kind of tabular format by later commentators like Bhaskara, to use these quotients in reverse order to substitute back through the steps you took. Each backward step reconstructs the solution for the slightly more complex equation from the previous stage.
So you climb back up the ladder you came down.
That's a great way to put it. You reverse the pulverizing process, step by step, using the recorded information, the quotients, until you arrive at the integer values for the original x and y.
It sounds recursive, almost. And the source says it's guaranteed to work if a solution exists.
That's the beauty of it. It's not guesswork. It's an algorithm, a defined sequence of steps that guarantees finding the integer solutions if they exist. It demonstrates a really deep grasp of number theory, the properties of division and remainders.
Amazing. And Aryabhata presented this in the Gaṇitapāda, the math section, but others built on it later.
Yes, absolutely. Mathematicians like Brahmagupta, who came later, refined the method, explained it more fully, and extended its applications. It became a standard, powerful tool in the Indian mathematical toolkit.
Which leads perfectly into our next bit, segment 4. Significance in ancient and medieval math. So this wasn't just a flash in the pan, it stuck around.
Oh, definitely. The source makes it clear this is a cornerstone technique for centuries in India. For anyone doing serious astronomy, needing to make accurate calendars, or predicting long-term planetary cycles, the Kuṭṭākāra was indispensable.
The go-to method for these crucial calculations.
Exactly. It offered reliability. You could trust the results if you followed the steps correctly. It really represents a high point in Indian algebra, particularly for tackling these Diophantine equations. That's the technical term for equations where you seek integer solutions.
And how did it compare to what other cultures were doing around the same time, say the Greeks or Babylonians?
Well, the Greeks certainly worked on related problems. Diophantus himself is famous for these types of equations. But the Indian approach with the Kuṭṭākāra was arguably more systematic, more algorithmic. It provided a general method guaranteed to work, rather than relying on specific clever tricks for individual problems.
So maybe more like a programmable solution.
In a sense, yes. It really highlights a strength in algorithmic thinking, a procedural approach to problem solving that was very characteristic of Indian mathematics. The source also notes related work in China, with the remainder theorem, showing these ideas were being explored globally. But the Kuṭṭākāra stands out for its specific formulation and application within the Indian astronomical context.
A real strength in number theory and algorithmic methods.
Undeniably.
Okay, fascinating history. Now let's bridge the gap to today. Segment 5, modern echoes. How does this ancient pulverizer connect to our world?
Well, the direct lineage is through number theory. the study of integers, their properties, divisibility, remainders, prime numbers. And yes, finding integer solutions to equations like ax plus by coc, Diophantine equations, is still a fundamental part of number theory today.
And number theory isn't just for pure mathematicians anymore, is it? The source connects it to something very modern.
Right. Cryptography, secure communication. It seems like a huge leap, maybe, from ancient astronomy to protecting your email or online bank details.
It does. How does that connection work?
Modern public key cryptography, the systems that secure so much of our digital lives, like RSA, Diffie-Hellman, relies heavily on mathematical problems that are easy to compute in one direction, but incredibly hard to reverse unless you have some secret information.
Like multiplying two huge prime numbers is easy, but factoring the result back into the original primes is hard.
Exactly. That's one example. Many of these systems are built on the properties of prime numbers and, crucially, on modular arithmetic, which is precisely the mathematics of remainders. That's at the heart of the Kuṭṭākāra and the Chinese remainder theorem.
So working mod, like we talked about with the remainder problem.
Precisely. Operations like finding modular inverses, solving linear congruences, which, remember, are related to ax plus by Koot-taa-KAA-ra via the Koot-taa-KAA-ra's principles. These are fundamental building blocks in cryptographic algorithms. The difficulty of solving certain number theory problems forms the basis of the security.
So the very same kind of mathematical thinking, manipulating integers, understanding remainders, finding specific integer solutions or related values that Aryabhata used for planets, is now used, albeit in a much more complex form, for digital security.
It's an incredible through line, isn't it? The context is totally different: planetary alignments versus data encryption. But the underlying mathematical principles involving integers, remainders, and algorithmic solutions are deeply related.
It really shows how fundamental these mathematical ideas are.
It does. Aryabhata's algorithmic approach, his deep dive into number theory to solve practical problems of his time, contributed to this vast stream of mathematical knowledge that, centuries later, provides the tools for tackling entirely new challenges, like securing our digital world.
So in a way, the thinking behind the Kuṭṭākāra helps keep my online messages private.
In a very real, albeit indirect sense, yes, the mathematical foundations are shared.
That's a fantastic connection. Okay, let's wrap this up. So recapping this deep dive, Aryabhata's Kuṭṭākāra algorithm clearly stands out. It wasn't just some obscure mathematical footnote.
Not at all. It was a brilliant, systematic method for solving linear, indeterminate equations, finding those crucial integer solutions.
And absolutely vital for his astronomical work, right? For predicting alignments, fixing calendars, basically making sense of cosmic cycles.
Exactly. A practical tool born from astronomical necessity, but also a major contribution to the history of algebra itself. It really showcases that algorithmic power we talked about.
A mathematical code, almost, that worked across time. Now, looking ahead, the source material for our next deep dive points towards what happened after Aryabhata in India.
Yes, the intellectual developments, the debates.
Right, the controversies, different schools popping up, and especially the role of commentators, how they interpreted and built upon earlier work. Should be fascinating to see how science and math evolved through discussion and, well, argument.
It promises to show how knowledge isn't static, how it gets debated, refined, passed on. Looking forward to that.
Me too. And maybe a final thought for you, our listener, to ponder from today's discussion. Just think about how something seemingly abstract, like finding whole number solutions to an equation developed centuries ago for problems like planetary positions, can echo today in something as critical and modern as securing our digital information. It really makes you wonder what foundational ideas we're developing now might enable centuries down the line.
A powerful thought. The enduring and often unexpected relevance of fundamental mathematical ideas.